Chapter 3 is about the vector space Rn. That means a set of all vectors with n components. So R10 would be the set of vectors with 10 components. Chapter 2 deals with R2 and R3, and these spaces are special because you can geometrically visualize what's going on in 2 and 3 dimensions. And then in the next chapter, when we talk about vectors in R5 and adding vectors and vectors being orthogonal and scalar multiples and so forth, it helps a whole lot to imagine what's going on in R2 and R3 geometrically, because in R5 and R10 you can't really visualize what a vector looks like in R3. So chapter 2 is basically a lot of this is going to be a review of what you had in maybe high school geometry. It's almost exactly what we covered the first 5 sections of Chapter 11 in Calculus 3. So if you've had Calculus 3, this should be, all of Chapter 2 will be a review also. So Section 1 starts talking about vectors in R2. And a vector in R2 is a two-dimensional vector, 2 components, x, y. And a vector has a length and a direction. So if you tell me what direction and how long the vector is, that uniquely specifies the vector. It doesn't matter where it starts. So if you take this vector here and you move it over here and it's still pointing in the same direction, same length, it's the same vector. And you can find the components of the vector by subtracting the point, this point, the head point minus the tail point. You add vectors algebraically just by adding their components. Geometrically, what happens when you add 2 vectors? Well, let's say this vector u and this vector v, you move them to where they still have the same direction and magnitude, but they start at the same point. So we move v to where it starts, where u ends, and then u plus v is going to be the sum of those 2 vectors. It'll be the third side here. So if u is this vector, it's the same as this vector here. We just moved it. Actually, we didn't move it. We moved v over here. If you put them head to tails, then the resulting arrow is the sum of the vectors. If you multiply a vector by a scalar, it's going to have the same direction or opposite direction if it's negative scalar, and it just changes its length. So if this is the vector u, then 3u would be 3 times as long in the same direction from here to here. Minus 1.5u would be in the opposite direction and 1.5 times as long. And this, the vector addition scalar multiplication actually works for R3 also. Adding vectors in R3 or multiplying by a scalar, it's the same thing. So in R3 you still add vectors, 3-dimensional vectors, which are now arrows with a certain direction in 3 space and a certain length. You add them head to tail the same way. And scalar multiplication, same thing. 3 times u is just going to be a vector in the same 3-dimensional direction as u, but 3 times as long. The vector I represents 1, 0 vector, j is 0, 1, and then in 3 dimensions, I is 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. So in 3 dimensions, I is the unit vector, the vector of length 1 in the direction of the x-axis, j is in the direction of the y-axis, k in the direction of the z-axis. So any vector u1, u2, u3 can be written as u1 times I plus u2 times j plus u3 times k. And so those are just 2 different ways of writing the same vector. In 2 dimensions, I is just 1, 0, j is 0, 1. And we'll talk about unit vectors. A unit vector in the direction of u, whether this is 2D or 3D, you just divide by the length of u. You multiply by the scalar 1 over the length of u, and that gives you a vector of length 1. If u is length 5, you divide by 5. Now it has length 1 in the same direction. So unit vector in the direction of u, you just divide by the norm of u. And by the way, the norm, as you probably know, is the square root of sum of squares of the components. So the length of a vector in 3 space is the square root of u1 squared plus u2 squared plus u3 squared. In 2 space, of course, it's just square root of u1 squared plus u2 squared. And by the way, that doesn't come directly from the Pythagorean theorem. It comes indirectly from it. You have to do a little bit of work to prove that this is the length of a vector, but that's the length of a 3D vector, and we're going to define the length of a 5-dimensional vector to be the square root of the sum of squares of the 5 components. It doesn't make any sense anymore as length in R5, but we're going to define it the same way. The homework in chapter 2 and 3, section 1 and 2, should be pretty simple. They're just adding vectors and taking scalar multiples of them. And let's look at this. For example, it says take the vector 1, 0, 1 and find another vector which has the opposite direction and the length of the square root of 32. Well, you take v and divide by its length, which would be the square root of 2. That'll be a unit vector in that direction. Then you multiply it by the square root, multiply that by the square root of 32. That'll give you a vector with the length square root of 32, but then multiply by -1 because you want the opposite direction. Okay, section 3 is about the dot product and cross product. Those are, we've talked about adding vectors and multiplying by scalars, but how do you multiply vectors? Well, there's 2 different kinds of ways to multiply vectors. We're going to talk about both of them, the dot product and the cross product, sometimes called the scalar product and the vector product, because the dot product gives you a scalar, just a number. The cross product gives you a vector, and they're very different ways of multiplying vectors, but both useful geometrically. And so first, the dot product. The dot product of 2 vectors in R3 is just the first component of the first vector times first component of the second plus second component of the first times second component plus third component times third component. And in 2 dimensions, you just leave off the last term there. Now, the main thing that makes dot products useful is that the dot product of u and v is equal to the length of u, the norm of u, times the norm of v, times the cosine of the angle between them. And that's what we're going to prove now. That's important because it allows us to find the angle between 2 vectors, 2 3-dimensional or 2-dimensional vectors. This is very useful in finding the angle between 2 vectors because it's easy to calculate the dot product, and it's easy to calculate the norms. The norm of u is just square root of u1 squared plus u2 squared plus u3 squared, norm of v. And so you can solve for cosine of theta. So this is an important formula. Here's the definition of the dot product. And by the way, the dot product is defined for 10-dimensional vectors, 2 10-dimensional vectors. It's pretty obvious. It'd just be u1, v1 plus u2, v2 up through u10, v10. So you can define a dot product between vectors of any length. They have to be the same length, of course. Can't take a 2-dimensional and 3-dimensional vector and dot product, but any 2 vectors of the same length, you can take the dot product in the same way. And we're going to show that at least in 3 dimensions and therefore in 2 dimensions, this formula holds here. And that's what makes it useful, because you can use that to find the angle between vectors. Okay, so now we're going to prove this formula here, that the dot product of 2 vectors is the length of u times the length of w times the cosine of the angle between them. So we've drawn this, here's the vector u, here's the vector w, and we're going to prove this formula a little bit of an indirect way. These are 3-dimensional, we're assuming these are 3-dimensional vectors. We've drawn them in 2 dimensions, but this is just the plane that, whatever plane the 2 vectors are in. You put them tail to tail here. Then here's how we prove it. The vector w minus u is this third side here. See, if this is u, this is w minus u, you add them and you get u plus w minus u, which is u plus wu minus u is equal to w W. So this is this third side here is W minus U. And the length of that vector, that third side, by the Pythagorean theorem, is the length of this squared plus the length of this squared. Well, what's the length of this? Well, it's the whole length of U minus this distance, which is length of W times cosine of theta. So this is the whole length of U minus W times the cosine of theta. Actually, if U is shorter than W, then it's going to look like this, and then this is going to be the other, it'll be this minus that, but we're going to square it, so it won't matter. So we'll draw it as if U is longer than W here. So this segment here is the length of U minus length of W times cosine of angle between them. The length of this is length of W times the sine, and so the square of that length is equal to the first side square plus other side square by Pythagorean theorem. We square this out to get length of U squared minus 2 length of U length of W times cosine of theta plus length of W squared cosine square, and then square that, get length of W squared sine square. Add these two together, cosine squared plus sine squared is 1, so that just gives length of W squared, and then we have the other two terms here. So this is one way of expressing the length of this third side here. Now, another way of expressing it, well, the length of any vector squared is the dot product of that vector with itself. I guess I didn't mention that last section, but on any vector v, the norm of v is the square root of v dotted with itself, the sum of squares of the components of v. Therefore, the norm squared of any vector v is that vector dotted with itself. So the length of W minus U is W minus U dotted with itself. And you multiply that out, dot product is distributives, and that gives you U dot U plus W dot W minus the two cross products minus U dot W twice, because U dot W is the same as W dot U. So that's equal to that, and then the length U dotted with itself is the length of U squared, W dotted with itself the length of W squared, so we have that. So they're both equal to the square of the length of the third side, so this has got to be equal to that. So we set them equal to it. This is the formula we got for the length of the third side. Basically using the law of cosines. In the book they just say the law of cosines that you learned in high school gives you this formula here, but you probably don't remember it, so I basically derived the law of cosines for you. That's what this is. So the length of the third side by law of cosines is that, which is kind of a generalization of Pythagorean theorem. It says the length of the third side squared is the sum of the length of the other two squared minus 2 times that. But if theta were 90 degrees, that would be 0. And so the case when W and U are orthogonal, that's just the Pythagorean theorem. So the law of cosines is kind of a generalization for where the two vectors aren't orthogonal. Anyway, so that's the length of the third side squared, but then we also showed by just multiplying out W minus U that it's equal to that. Now you cancel the U squared, W squares, and you get this is equal to that, divide by minus 2, and there's the formula. So if I lost you in the derivation, it doesn't matter too much. The important thing is you need to remember this formula and know how to use it, and it's mainly useful for finding the angle between two vectors, because everything else is easy to calculate. The dot product of U and W is just a question of first component plus second component, and so forth if it's three-dimensional. And the norm of a vector is easy to calculate. The angle between them is not easy to calculate, but you can use this formula and find the cosine of theta and therefore the theta. So this is the main thing the dot product is useful for. It's called a scalar product because the dot product of two vectors gives you a number, not a vector. So here's an example of the use of that formula. Here you've got two vectors in 3D, and you want to find the angle between the two vectors. And that's something that's actually pretty hard to calculate directly. If you try to do this geometrically, it's going to be pretty complicated, but with this formula it's easy. You just calculate u dotted with v. That'd be 1 times 4 plus 3 times minus 1 plus minus 2 times minus 3. Calculate the norm of u, which is square root of 1 squared plus 3 squared plus minus 2 squared. Norm of v, square root of 4 squared plus minus 1 squared plus minus 3 squared. And divide the two, and you get cosine of theta is equal to the dot product, which was 7 over this. Comes out to be 0.366, and then just use your calculator to find theta, 68 degrees or 1.19 radians. Notice that if the two vectors are orthogonal, that means the dot product is 0. The cosine of theta is 0. If the angle between the two vectors is 90 degrees or minus 90 degrees, the cosine is 0. The dot product will be 0. So the dot product between two vectors is 0 if and only if they're orthogonal in 2 or 3 dimensions. And we're actually going to talk about the angle between two 10-dimensional vectors. We'll define it. We'll basically use this formula to define the angle between two 10-dimensional vectors. And no longer makes sense geometrically. What's the angle between two 10-dimensional vectors? Who knows? Well, we know using this formula, but that's just a way to define it. And we'll still say that two vectors are orthogonal if their dot product is 0 in 10 dimensions, even though it doesn't make any sense geometrically to say that two 10-dimensional vectors are orthogonal. 10-dimensional vectors don't make any sense geometrically. But we can still use this formula to find the angle between two vectors of any length, because the dot product is still easy to calculate, the norms are still easy to calculate. So for example, u and v, if you take the dot product, it's 2 times 1, which is 2, minus 9 plus 7, that's 0. Therefore, u and v are orthogonal because from this formula, if the dot product is 0, it doesn't matter what these are, the cosine of theta is going to be 0, which means theta is plus or minus 90 degrees, pi over 2. Okay, now let's talk about the other way to multiply vectors, the cross product. And as we said, the dot product is defined in R2 or R3 or R4 or 5. It's just going to be u1 times v1 plus u2 times v2, etc., down through the 10th component. So if you have two 10-dimensional vectors, you can still take their dot product. So dot product is defined in any Rn. The cross product is strictly in 3 dimensions, but since we live in a 3-dimensional world, it's very useful. So cross product, remember, is only defined for 3D vectors. And here's the definition, and notice that it's a vector. So you take the dot product of two vectors in any dimension, you get a number, a scalar. Take the cross product of two 3-dimensional vectors. You can't take the cross product in 2 or 4 dimensions. 3-dimensional vectors, and you get this vector of 3 components. Now that's a little hard to remember, this formula here. So there's a way to remember how to take the cross product that's a little simpler. So look at that. So here's a way to remember u cross with v. These are two 3-dimensional vectors, u and w, sorry. My v's look too much like my u's, so I use w. So u cross w, if you can just remember this formula right here, there's the 3 components, but that's pretty hard to remember. So easier way to do it is to write down a 3x3 matrix where the first row is ijk. Remember, I is the vector 1, 0, 0, j is 0, 1, 0, k is 0, 0, 1. And the second row, put the 3 components of u. The third row, put the 3 components of w, and the order does matter, as we'll see. And you take the determinant of that. And we're assuming you remember how to take determinants. Maybe you don't, but the determinant of a 3x3 matrix is calculated as follows. You take the I times the determinant of the 2x2 matrix you get when you throw out the row and column that I is in. So it's I times, now you probably do remember the determinant of a 2x2 matrix, that's u2 w3 minus u3 w2. So it's I, the vector I, times the number u2 w3 minus u3 w2. And then you go minus j, you just always alternate in sign, plus I minus j plus k. So you plus I times the determinant of what you get when you throw out the row and column it's in, minus j, just remember always plus I minus j plus k, minus j times the determinant of the 2 by 2 matrix you get by throwing out the first row and second column. So u1 w3 minus u3 w1, which times minus j, then plus k times the determinant of this 2 by 2. We throw out the row and column it's on u1 w2 minus u2 w1. And so this is the coefficient of I is the first component. The coefficient of j with the minus sign here is the second component. Coefficient of k. So two different ways of writing the same vector. So that's a little easier to remember than, if you can remember this formula directly, fine, but I can't. So I calculate cross products by writing out ijk and then the first vector here and the second vector there and take the determinant. We'll talk about determinants later in chapter 4, I guess, but I'm assuming you at least know how to calculate the determinant 2 by 2, and now you know how to calculate determinant 3 by 3. Okay, so what is the cross product good for? You take the cross product of two three-dimensional vectors, has to be three-dimensional. You get another three-dimensional vector, and here's how you remember the formula. What good is it? Well, u cross w is a vector which is orthogonal to both u and w. And that's easy to show, fairly easy to show. Let's just take the dot product of u cross w with u and show that that's 0. And that will show that the vector u cross w is perpendicular to u. And that's just a question of writing out the dot product of this three-dimensional vector with u1, u2, u3. In other words, first component of u cross w times first component of u plus second component of u cross w times second component of u plus third component of u cross w times third component of u. And now you have to just multiply all this out and simplify, and things cancel in pairs here. Like here's a u1, u2, w3, and here we have a minus u1, u2, w3, so that and that cancel, and they're going to cancel in pairs and you get 0. So that shows that the cross product is orthogonal to u, and if you place u by w, you'll still get 0. And you can show that, so the cross product is orthogonal to both u and w. So this is one thing it's useful for if you want to find like in the next section, we'll do this. When you want a vector which is orthogonal to two vectors, you just take their cross product, and that'll give it to you. So now we know that the direction of u cross w, we know it's orthogonal to both u and w. There's only two directions that can be, depending on which, up or down. But what about the length? So we know it's a vector perpendicular u and w, but how long is it? Well, that's what we're going to find out here. The length of u cross w squared is equal to, well, just take the first component squared plus second component squared plus third component squared. That's, here's the three components, this squared plus this squared plus this squared. That's the length of u cross w. Now, here's the really hard step, and we're going to leave it as an exercise for the user because it's too messy. But it's just straightforward algebra. You can show that this complicated thing after you square it out is the same as this line here, which is u1 squared plus u2 squared plus u3 squared, quantity times w1 squared plus w2 squared plus w3 squared, minus u1 w1 plus u2 w2 plus u3 w3 squared. So this is not at all obvious. You have to multiply all that out. But it's just straightforward algebra. All you have to do is multiply it out, and you'll see that everything cancels and these two are equal. And so that's the hard step, but can be shown that. So what is this? This is the norm of u squared. This is the norm of w squared. This is just the dot product of u and w, quantity squared. So it's equal to that. And now we use the fact that u dotted with w is the length of u, length of w times cosine of the angle between them. So we write that for u dotted with w as length of u, length of w, cosine angle between them, that whole thing squared. And we get u, quantity, u length squared, w length squared, cosine squared. Factor out the u squared, w squared, and we have 1 minus cosine squared, which is sine squared. And so this, the length of u cross w is equal to this. Take the square root of both sides and you get the length of u cross w is the length of u times the length of w times, well, the absolute value of the sine of theta, because the square root of sine squared is not sine of theta, it's the absolute value of theta. So now we know the direction of u cross w, it's perpendicular to both u and w, and now we know the length. Now this looks a lot like the formula for a dot product. We had dot product of u and w is length of u, length of w times cosine of the angle between them. But this is not saying that u cross w is equal to that. It's u cross w is a vector, it's not a scalar. The dot product u dotted with w is length of u, length of w, cosine of theta, exactly equal to it. But this, we're saying that the length of u cross w is that, not that u cross w is that, so don't get confused. So the cross product is perpendicular to both vectors, and there's its length. Okay, so a dot product is useful because it allows you to find the angle between two vectors in 2 or 3 dimensions. In 3 dimensions, particularly hard without the dot product. And it even can be used defining the angle between two vectors in R5 for any length we want, even though it doesn't make any sense. Angle between vectors doesn't make any sense geometrically anymore. Now, what's the cross product good for? Well, we just said one thing it's good for is finding a vector that's perpendicular to 2 other vectors, and that will be useful in the next section. But here's another application, it's finding the area of a parallelogram. So let's say we have this parallelogram here. What's the area? Well, you know from geometry that it's the length of the base, AB, times the height. But the height is the length of this vector times sine of theta. So the area would be the length of AB times the length of AC times the sine of theta. In other words, length of AB times the height, which is length of AC times sine of theta. And that, we just showed, is equal to the length of the 2 sides, AB and AC. Those are 2 adjacent sides of the parallelogram. And so the area is just going to be the magnitude of the cross product of those 2 sides. And see, this is fairly easy to calculate, easier than the area directly. Like this could be a parallelogram in 3 dimensions here. You got 2 vectors out in 3D somewhere that are the 2 sides of a parallelogram. How are you going to find the area directly? Well, it's pretty hard, but using the cross product, it's not too bad. You just take the 2 side vectors, form their cross product, and then take the magnitude of that, square root of sum of squares, and that will be the area of the parallelogram. And notice you can also use that then to find the area of a triangle. Let's say the triangle ABC, because that'll just be half of the area of the parallelogram. So you just calculate the area of the parallelogram and divide by 2. So that allows you to get the area of a triangle in 3 dimensions. So imagine that A, B, C are arbitrary points out in 3 space, and you form a triangle by connecting the lines there. Now, how would you calculate the area of that 3D triangle? Well, using the cross product is fairly easy. You take this vector AB, this vector, take the cross product, which is a little bit of work but not too hard, and then take the norm of that, just a vector, so take the square root of sum of the 3 components, and that will give you the area of the parallelogram, and therefore cut it by half and you get the area of a triangle. Another application is the area of a parallelepiped. That's like a 3-dimensional parallelogram. So if you have 3 edges, U, V, and W, 3 adjacent edges of a parallelepiped, and you want the volume of that, well, it takes a little bit more work, but not much, to show that that's equal to the U dotted with V cross W, actually any 2 sides. So you take the cross product of any 2 sides and take the dot product with U, and that will be a number. Just take the, this means you have to take the cross product first. It doesn't make any sense to take U dot V. That's just a scalar, and you can't take the cross of that W, so you don't even need the parentheses here. U dotted with V cross W, you have to do the cross product first, otherwise it doesn't make any sense. So do the cross product of V and W, and then take the dot product with U, and the absolute value of that number will give you the volume of the parallelepiped. So that's a relatively easy way of finding the volume of a parallelepiped. Okay, the homework problems. Here you're supposed to find the angle between two-dimensional vectors. You just use the fact that u dotted with v is norm of u, norm of v times cosine of the angle between them. Everything's easy to calculate it. Solve for cosine of theta. These are two three-dimensional vectors, but same thing. It's still u dotted with v is equal to norm of u times norm of v times cosine of the angle between them. These problems, you're just supposed to calculate the cross product. Oh, by the way, I said that the order is important. U cross v is not the same as v cross u. U dotted with v is the same as v dotted with u, so dot product is commutative. The cross product is not. If you switch the u and v, well, you still got a vector, whether it's u cross v or v cross u, they're both perpendicular to u and v, and they both have the same length, because they both have the length of the norm of u times norm of v times sine of the angle between them. So if u cross v and v cross u are both perpendicular to u and v, and they both have the same length, how could they not be the same vector? Well, one of them is just going to be the opposite of the other. One's going to be in one direction, one's the other. So it does matter, but only changes the direction. Still the same length and still perpendicular to u and v. Okay, so these problems says find a vector that's perpendicular to both u and v. You just take the cross product, and that's it. Here, the area of a parallelogram, if you have two edges of a parallelogram, we use the formula we just showed, that the area of the parallelogram is the magnitude of the cross product. And then here, three edges of a parallelepiped, find the volume. Then you take the cross product of actually any two and dot it with the other. It doesn't really matter which two. It obviously shouldn't matter, because three adjacent sides of a parallelepiped, whether you call this u, v, and w, or u, v, and w, it's going to be the same volume. So it's not at all obvious that if you switch these u, v, and w around, take any two cross product and dot with a third, it's going to give you the same absolute value, at least. Maybe negative, but if you take the absolute value, it's going to be the same. So it doesn't matter which two you take cross product and you dot with a third. It'll give you in the absolute value, that will give you the volume of the parallelepiped. Oh, well, you remember I said it's left as an exercise to the user to show that the length of u cross v squared was equal to that complicated formula. Well, it is literally left as an exercise to you. You're supposed to show that complicated formula. It's basically grind it out, just calculate the norm of u cross v. Sum of squares is equal to sum of squares of u times sum of squares of v minus dot product u and v squared. And the rest is easy to show this. So basically this problem is to verify what I skipped. Also, problem 51, I just noticed, shows that cross product is not associative. And with this example here, it does matter whether you take the first two cross and then with the third, or the last two and cross with the first. So it's not associative.